of this session. Over to you, Paulo.
Right. Okay, is it okay now? Okay, very good. Okay, thanks Andrew, and thanks to the organisers for inviting me. I am Paulo Teixeira, and I'm going to tell you about some work I've done with Andrew, our chairman for this session, over a period of time. Phase behaviour of changing spheroids, what is this about? Well, it's actually about biaxiality. A number of speakers, and much greater than one before me, have told you why we are interested in biaxiality. The truth is we just love the stuff, whether it exists or not. So here we go. Right, so we all know that the archetypal liquid crystal forming mesogen is either rod or a disk, or at least most of them are. However, it was found that more flexible molecules, such as some polymers and something called tetrapodes, also exhibit liquid crystal phases. A tetrapode is what I show here, and basically it consists of 4 groups which are connected to a central core, and they can exist in various different conformations, of which I show 2 here. And it so happens that these interesting objects can exhibit nematic phases, and in particular they were found experimentally to exhibit the elusive thermotropic biaxial nematic phase. And I got these pictures from one of the authors of this paper. He didn't publish them, and he gave me permission to reproduce, so it's all okay. Right, so the mechanism here is that, well, by changing the shape of a molecule, they sacrifice some conformational disorder, but are able to achieve better packing and hopefully to pack into something like a biaxial nematic. So, well, what we set out to was to model this, to see what simple model we could come up with that would reproduce something like what was seen in this experiment. There you go. Now, model building. So, the idea we came up with, and which is not entirely original, is that a particle can exist in one of 2 states, which we call either a prolate or an oblate spheroid. Of course, these are much simpler than these, but of course, we wouldn't be doing anything like this. What we're doing is spheroids. Okay. The 2 states conformers are in chemical equilibrium, and we postulate that their energies differ by some prescribed amount. As it stands, the model, or the idea of model, is very similar to one that was put forward earlier by Vanakaras and co-workers. The way we implement the shape interconvertibility is a little different. And we also decided to use as our particle model the hard Gaussian overlap potential, which several other speakers have told you about. Basically, this is an approximation to hard ellipsoids, but it's convenient because the distance of closest approach is given in closed analytical form, and from this you can find fun and useful things like the orientational second virial coefficients and other things. And it also allows us to introduce shape non-additivity of different particle species through this parameter lambda, although in all the results that I'm going to show you, we did not. But that's something else, one other lever that we may wish to pull in the future. Right, so what do we do with this? First, we need to generalize it to more than one component. That's been done. And then, well, what do? You write a free energy. So here it is. And it's this pretty much the simplest free energy a microscopic theorist could think of, which is just a second virial, except that you add at the end the energy penalties for converting a shape into a rod or into a plate. Well, you can see immediately that what is going to matter is the difference between these two energy penalties, epsilon r and epsilon p. And all the other things in this expression are pretty well known by now. These are the ideal gas terms, orientational entropy, rod exclusion volume, plate excluded volume, rod plate excluded volume, as explained there. And this theory without that term there has been successfully applied to hard rod plate mixtures by, amongst others, these authors here. Right. Okay, so first job, we need to get that, the excluded volume of a rod and a plate. Oh, I can use this, yes. And here it is. You can find it in an analytical form, and this is what it looks like. Okay, perhaps not very pretty, but it's effective. So there you go. This is what we're going to use, the rod and plate versions of that being already known. And again, the shape non-additivity, this is how one might introduce it, although, as I said, we won't be using it here. On. What do you do first? Before you start doing some heavy-duty numerical computations, you try something simpler, and pretty much the simplest thing that one can do in this context is bifurcation analysis. You look at instabilities of the isotropic phase with respect to any type of pneumatic phase, and it's given by this expression there, where the XR and XP are the number fractions of rods and plates. That's row rod divided by total row and row plate divided by total row. This gives you the instability of the isotropic phase with respect to any pneumatic phase, and if in addition this other relation is also satisfied, then the pneumatic phase in question is biaxial. Just a few words again of justification for why this is the model we're using. Well, hard Gaussian overlap particles, HGOs, look a bit like ellipsoids, so maybe with a little bit of luck they will not want to go smectic, although we didn't look at smectic phases here. And moreover, this, as we will see, it's a kind of mixture. The two shapes can interconvert, so what you're going to end up with is a mixture of rod and plates, possibly of different number fractions. And the rest of it is just technical details. To do this kind of analysis, you need to expand your orientational virial coefficients in terms of the usual Legendre polynomials, so you can get some results for that. Okay, so now on for some pictures, the first of some pictures. This is the bifurcation, the instability density, and I wanted to concentrate on that line and this line, which are actually one on top of the other, and they go right through there. And what this means is that if there is no energy penalty, or if the energy penalty for going rod or going plate is exactly the same, that's rods and plates are equivalent, then you're unstable with respect to the pneumatic phase. The isotropic phase is unstable with respect to the pneumatic phase at this density as a function of rod elongation, and the instability is with respect to biaxial pneumatic. If this is non-zero, that is, if you favor either rods in these two cases or plates in these latter two, then the two lines are not on top of each other, which means that your instability is with respect to a uniaxial phase, either N plus rod type or N minus disc or plate type. Okay, so this is all very good, but let's do some more serious, not that this is not serious of course, but let's do some different calculations now. So we move on and do some numerics, but not the fully numerical version yet. We stop at second order in Legendre polynomials, so we do what's called the L2 approximation, which is also described by Amparo Galindo in her talk a few days ago. So what we do, you have a free energy. What are you going to do with the free energy? Yes, we minimize it. There you go. Equate chemical potentials of rods and spheres. Then for the cranks, get out some results for these orientational order parameters, which allow you to identify which phases you get. These are limiting values of those order parameters. This is what you get, strictly speaking, in the limit of zero temperature if this were a thermotropic, and the limit of infinite density because this isn't a thermotropic. But they allow you to identify which phases you get out of your calculations. And we have chosen as our z-axis the axis of orientation of the rods in the rod-like pneumatic, uniaxial pneumatic phase, as is usually done. For more details on these order parameters, here's the relevant reference. And what do we get? Well, now we have to play with numerics, and numerics, of course, involves solving things iteratively, and that involves having some initial guesses, and this is how we get our different solutions. So, I forgot to say, let's go back for a moment, that we assume that rods and plates have the same volume, and in addition to that the elongation of the rod is 1 over the elongation of a plate. Okay, so the resulting phase diagrams that we get will be very symmetric. Go on. Okay, so this is the uniaxial solution, the N uniaxial plus the rod-like or calamitic pneumatic phase that you get on increasing your density from isotropic, and this is where your rod uniaxial order parameter takes off, and your uniaxial order parameter for disks for the plates also takes off. Well, one is positive, the other is negative, and biaxiality is there, plonk at 0. On this side you have densities of rods, densities of plates, and fraction of rods. So you see that in the isotropic phase they're equimolar, but as you go into the rod-like pneumatic phase, then rods become the dominant species and the density of plates goes to 0. And let me emphasize that in this case neither of them is favored by this energy penalty that I mentioned. This is the diagram for delta epsilon 0. Okay, so this comes about just as a result of interactions between the rods and the plates. And we have something similar for the disc-like uniaxial pneumatic, except that these now are what they should be if we have a disc-like uniaxial pneumatic phase. And well, they take on these values because, as I showed you, we took the we chose our reference frame such that the z-axis is against the is along the direction of preferred orientation for rods in the rod-like phase. If we were to do it, I didn't want to show that yet. Right, if we had chosen the frame differently, then what you would see would be something like that. But now this would be the order parameter for rods, and this would be, the order parameter for plates, and this would be the order parameter for rods. So the fact that the order parameters are all non-zero here does not mean that this phase is biaxial. It is not. It means that we chose the wrong frame to describe it. But what you see here is that, unlike before, this phase is now rich in rods. It's equimolar in the isotropic phase. As soon as you enter the pneumatic phase, the rod density takes off and, well, just goes all the way up to practically 1. And we can also find a biaxial phase. There you go. Now all the order parameters are what they should be in the limiting case of high densities for the biaxial phase, and it is strictly equimolar in that neither shape dominates. This is the density of rods on top of the density of plates. So it's looking good, except it isn't, because it's only metastable. If you plot, yeah, there you go. That's life. Right, so if you look at the chemical potential, also known as the Gibbs free energy per particle, what you find, black line is the uniaxial phase, red is biaxial, blue is isotropic, and the Gibbs free energy per particle of the biaxial pneumatic phase is always higher. There you go. And it doesn't get better even if you take elongation up to 20. Now, it may be there are other things we can do about it, but in this kind of approximation, going to 20 will not help. So let's just very briefly review what might. Okay, so this is just what we've done. What haven't we done that we might do? Well, we could try going beyond this L2 approximation, which is admittedly a bit cheap. So we could do the full numerical calculation, and we saw from Amparo Galindo's talk that this does make a qualitative difference sometimes. So this is the next thing to do. It's also interesting to look at what happens when you do set a penalty for interconverting rods and plates. I've started work on that, but it's a bit bewildering at the moment. There's lots of things that can happen depending on how exactly you choose your initial guesses, so I'm still a bit lost there. Nothing else works. We could try playing with shape non-additivity, although at the moment we don't have a good feel for how that might help. Okay, that's it really. Thank you to the Isaac Newton Institute, to the people, oops, didn't want to show that yet, to the people who pay for my travel, to my bosses who allowed me to not teach for a semester and be here instead, and finally for the more or less mandatory shameless commercial plug, and that's it.
Thank you very much. Any questions?
I don't even know.
Sorry.
Next year.
Oh yeah, this is next year, by the way, if I might just add. So if any of you has nothing better to do end of July, please consider coming over. Lisbon's not too bad that time of the year.
Please, yeah, another question.
Paulo, you consider the case in which a rod and plate have the same volume.
They have the same volume, yeah.
What happens if instead of this you consider a case in which have the same as two?
Oh, they also do actually. Yes, in this approximation they also do, yeah.
Okay. So you did density functional
Yeah.
starting from the isotropic and also having pneumatic uniaxial as a background?
Oh, you mean the bifurcation stuff?
Bifurcation?
No, the bifurcation is just relative to the isotropic.
Only.
Yes.
So you still may have biaxial phase just bifurcating from the pneumatic uniaxial.
Absolutely, yeah, it's not excluded, certainly not
It
excluded.
would be worth checking that.
Yes, we will, yes.
Any other questions? In that case, Hannah, thank you very much indeed.